Hello, my name is Douglas Rumbaugh, and today I wanted to talk a little bit about propositional logic. This is a bit off the beaten path for this channel, but it's very important in the world of computer science, and I think it's worth talking about. So I want to, over the next couple of videos in this particular series, talk about propositional, and then we'll move on to predicate logic as well. And depending on how that's received, I may continue to do these more mathematically oriented videos. My ultimate hope is, of course, to have the mathematically oriented videos serve as the prerequisite, quote unquote, material for a future series on computer programming, which is, of course, built upon all of this stuff. So let's get started with propositional logic, which you will find is very useful in terms of both interpreting program requirements and designing logic flows through programs, as well as in everyday life. I hesitate to say that, but it's very true. Applying the principles, the mathematical principles of logic, can help you make better decisions in life. So with that out of the way, let's dive right into it by discussing what exactly do we mean by a proposition. Because this is propositional logic, so we are apparently going to be doing something with propositions and something with logic. The proposition part of it is the set of statements to which the rules that govern this particular system of propositional logic apply. Now, a proposition is a statement that meets two criteria. The first criterion, I suppose, is that it's a declarative statement. Okay, so it has to be a statement of fact. And I use fact not to mean something that's true, but I use fact to mean something or a description of something. So it is raining outside is a declarative statement. The second part of it, and the perhaps most important and most subtle in terms of what is a proposition and what isn't, is that it has to be either true or false, but it cannot be both. And this particular piece is very important. So what this means is that for a proposition, well, I should say for a statement to be a proposition, it must be able to be resolved to either yes, this statement is true, or no, this statement is false. If it's sort of an in-between wishy-washy area, then it is not a logical proposition, and you cannot apply these rules that I'm going to talk about later to that particular statement, which is very important. So let's just throw down some examples of propositions. It's all well and good to define them, but sometimes practical examples are of a little more use. So I mentioned earlier, it is raining. Or it will rain today, or what have you. This is obviously a proposition. It's a declarative statement. It's a statement of fact. It's raining. And it's true or false. You can look out the window, and if it's raining, then yeah, it's true. Or if it's not raining, then it's false. Another one would be, say, how about, this is a classic, 1 + 1 = 3. Or for you Orwell fans, I believe it's 2 + 2 = 5. They're both dead wrong, of course. 1 + 1 does not equal 3, and 2 + 2 does not equal 5. Yes, even if you're in room 101. But the important distinction here is that they are a declarative statement. It's a statement of fact, 1 + 1 = 3. And it's false. You can you can definitively say that this statement is false. And as a result, these are valid propositions. They're false, but they're valid propositions. So how about a slightly trickier one here? X squared is greater than or equal to 10. Is this a proposition? Well, let's see. It is a declarative statement for sure. It meets the first criteria. So we'll give it a nice little check mark there. However, is it true or false? Well, that depends. It depends on what x is, right? If we were to say, okay, well, let's go ahead and say x is equal to 2, well then 2 squared is 4, which is definitely not greater than or equal to 10, so it's false. But if we don't give x a value and we just leave it open like that, then it's not a proposition, because it cannot be reduced to either true or false. Depends on what x is. The moment we give x a value, then yeah, it becomes a proposition. So this is a proposition. You can plug the 2 in there and you're good. But without giving x a value, you cannot call this a proposition, because it isn't. It's just it's a statement. It's an algebraic expression. Great. So why is this useful? Well, because of our nice little stringent requirements here, we can do something kind of cool. Because it has to be true or false, and it can only have one value, we can substitute a variable for our particular statement. So for example, we could call the statement, the proposition, if you will, it is raining. We'll call that P. And P can have one of two values. It can be true or it can be false. And this allows us to easily manipulate these propositions and avoid sort of the wishy-washy nature of writing in the English language or any language. There's always ambiguity there. But we can use notation to get around that and be very strict about what we mean. And it also allows us to solve more complicated systems of statements and propositions. So let's talk a little bit about the next step of complexity, where this variable assignment methodology becomes very, very useful. We're talking now about compound propositions. I was going to say prop, you know what I mean. Okay, now a compound proposition is multiple propositions that are connected together. An example would be, say, the statement, it will rain today. This statement is a proposition. We can confirm that. It's a declarative, and it can be said to be either true or false, but it won't be both. It'll either rain or it won't. Or, it will rain tomorrow. Here we have a second proposition. Again, it is a declarative statement, and it is either true or false. Aha! So we have two propositions that are linked together with the word or. And we call this or a connective, because it connects the two propositions. I've always been very fond of the way mathematicians name things. They're usually pretty good about it. A connective connects things. So this is a compound proposition. And what we can do is we could say, okay, well, this first proposition, it will rain today, that's P. In this one, it will rain tomorrow, is Q. So we can represent this whole sentence as P, a connective, Q. Now we have different symbols that represent each connective. So in this case, or is a connective, but it is what is known as a disjunction, which is a fancy word for or. And the symbol for a disjunction is a V. So P, disjunction, Q. Now note, there is a distinction to be made here, because there are two kinds of disjunction if you think about it. It will rain today or it will rain tomorrow. What do we mean by or? There are two possible ways you could interpret this sentence. It will rain today, or it will rain tomorrow. But if it rains tomorrow, it's not going to rain today. And if it rains tomorrow, if it rains tomorrow, it's not going to rain today. And if it rains today, then it won't rain tomorrow. In this case, where only one of the two options is true. Oops, let me find myself here. And that looks a little too French for my taste, so we'll spell true correctly here. All right, so the case where only one option can be true, that's known as an exclusive disjunction. Or it could be it will rain today, or it'll rain tomorrow, but it could rain both days too. And that meaning is known as an inclusive. So if it's one or both can be true, that's an inclusive because it includes the case where both of them are true. An inclusive disjunction. So this symbol here is the symbol for an inclusive disjunction. An exclusive disjunction is this, a plus sign surrounded by a circle, and an inclusive is our V. Okay. So it will rain today or it will rain tomorrow. Now let's solve it, so to speak. We're going to use what's known as a truth table. So for a truth table, we have our two propositions that make up our compound proposition. Okay. So P is a proposition, Q is a proposition. P, inclusive disjunction Q, is our compound proposition. Now the truth value, whether this sentence, it will rain today or it will rain tomorrow, is true or false, is going to depend upon P and Q, right? P can be true or false, Q can be true or false. And depending upon our different combinations of P and Q, our entire compound proposition can be true or false. Clean up some of these random dots laying around everywhere. Okay, so we have ourselves a table to fill out. Now, there's a special technique for this because we want to capture every possible combination. So in the case where we just have two variables, P and Q, we're going to have 4 rows in our truth table. And you might be thinking, oh, well, that's 2 squared. Yes, that is. And that's a general rule you can follow. The number of rows in your truth table is going to be n, and it will be equal to 2 to the power of the number of distinct variables in your truth table. We'll call that k. In this case, we have 2 variables. K is equal to 2. 2 squared is 4, so we're good. And you fill it out this way. So you would start with, let me get my full mouse here. Start with alternating every 1, true, false, true, false. Then you go to alternating every 2, true, true, false, false. Then you would double it again, true, 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 false, 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 if you had 3 variables, and so on. And you basically just incrementing by powers of 2. And that will get you every possible combination. If that doesn't make sense, just stay with me, and as we get into some slightly larger truth tables later, you might start to see what I mean. It's kind of hard to explain it. Where's my thing? There we go. Okay, so P or Q. This is an inclusive disjunction, which we defined over here as one or both. So over here we have both of them are true. which means our compound proposition is going to be true. Here, just one of them is true. That's fine. And here, just one of them is true. And here, neither of them are true. And that's our truth table. So what this truth table tells us is that the statement, it will rain today or it will rain tomorrow, the whole compound proposition will be true if it rains both today and tomorrow. It will be true if it rains tomorrow. It will be true if it rains today. And it will be false if it doesn't rain either day. All right. So let's look at some other connectives. We also have the, where am I here? We have the conjunction. Otherwise known as and. So using a conjunction, we can say, all right, well, it'll rain today and it will rain tomorrow. Now our conjunction here, our and, as I'm sure you can guess, this is going to be true when both propositions are true. And it'll be false otherwise. So let's represent our compound proposition in algebraic form. It will rain today is P. It will rain tomorrow, well, that's Q. And our entire statement, then, compound proposition, I should say, is P and Q. The symbol for and is an upside down V. I like to remember it as being and is the one that looks like an A, except it doesn't have the line in the middle of it. Minus A minus the center line. Or is the other one. So I'm sure by now you can guess exactly what's going on here. If we do our truth table for this, we have P, we have Q, and we have P and Q. And we'll just fill this thing out using the same pattern I mentioned above. And I'm sorry, my alignment is not the best, but you get the idea. Okay, so our definition of the conjunction is true when both propositions are true. It's over here. So P and Q are our two propositions. P is true, Q is true, P and Q, well, that's true. It's going to be false every other case, though, because they're not both true. So as you can see, and is a much stronger relationship than or. Or is true in 3 out of 4 cases. And is true in just 1. All right, let's talk about another one. This one's a little weird because it's still a connective, but it only works on one statement at a time. That's the complement. Otherwise known as not. Or you'll also see it called negation. Right? So here we have it will not rain today. Period. So we have our statement, it will rain today, P, and we have our connective, not. Because it only operates on one proposition, we call this unary. unary as in one. These other two up here, the disjunction and the conjunction, they are examples of binary connectives. Bi for two. They have two propositions associated with them instead of just one. So because we just have our one propositional variable here, we have P. Our truth table is going to have how many rows? If you said 2, then you're exactly right. Now the symbol for complement is this, not P. It's a little, I don't know what you would call it. So all it does is it flips it. If P is true, then the complement of P is false. And if P is false, then the complement of P is true. All right, moving right along. And this is just basically me running off definitions for now. Once we have a grasp of what the different connectives are, then we can begin to actually use them to solve problems. And that will come in the next video. So I'm running pretty long right now. Then we have the implication. This is an important one, and it's one that you will use a lot. Implication is if it rains today, then I will wear a raincoat. Okay, so an implication has the form if then. So if it rains today, then I will wear a raincoat. So we have P and we have Q. Now in this case, P and Q have special names. Because this if-then relationship has been discussed at length in formal logic, there are very complex formal names for it. So we call P the antecedent. And we call Q the consequent. And what this implication does, and for the record, the symbol for it is P and then an arrow pointing to Q. P implies Q. What it does is it says, all right, well, if P happens, then Q has to happen. What's important and what's subtle about this operator, and it's something that that we don't really think about a lot, and we'll often assume that it works this way in general, is it doesn't say anything about going the other way. So if we look at our truth table for this, we have P, we have Q, and then we have P implies Q. So once again, we're going to have 4 rows in our truth table. All right, so P implies Q. If P happens, then Q had better doggone well happen. So P is true, Q is true. We're golden. But now if P happens and Q doesn't happen, well, then we're false, because if it rains today and then I go out without my raincoat, I lied. This statement, if it rains today, then I will wear a raincoat, is patently false if I don't actually wear a raincoat when it rains. But these next two are where things start to break down a little bit and get kind of tricky. So what happens if it doesn't rain? If it doesn't rain, but I still wear my raincoat, is this statement up here wrong? Well, no. This statement says nothing about what happens if it doesn't rain. It only says that if it rains, then I'll go on and wear my raincoat. But if it doesn't rain and I still wear my raincoat, I wasn't lying. An example that I heard in once was pertaining to sports. If you were ever involved in athletics in high school or elementary school or what have you, probably college as well, but I don't know that this happens particularly much in the collegiate level. It's where your coach says, all right, guys, if you win the game, I'll take you guys out for pizza. That is very much an implication. If we win, then pizza. So, if you win, you get pizza. Great. If you win and you don't get pizza, you're going to be pretty upset. That's false there. He lied to you. But if you lose, if you don't win, I should say, and he still takes you out for pizza, he didn't lie. He's just being kind of nice to you. So in the case where the antecedent P is false, but the consequent is true, the whole implication is considered to be true. And likewise when they're both false. So the general rule with implication is that if the antecedent is false, the implication is true, regardless of what the consequent is. You don't even have to look at it. As soon as you see that the antecedent is false, then the implication as a whole is going to be true. Likewise, if the consequent is false and the antecedent is true, then it's false right here. And of course, if they're both true, then you're good. There's a slight variation on the implication. It's called the by implication, which is a little more stringent. So the by implication would be something along the lines of, I will wear a raincoat if and only if it rains. So here we're a little bit more stringent. If and only if. And because of the way I used if and only if, this is kind of flipped around. Raining is still P and the raincoat is Q. So let's take a look at the truth table for this. For the record, of course, the notation would be P, Q, and then our connective is the biconditional, is what this is known as. And it's an arrow, or a double-headed arrow. Arrow pointing, P implies Q, and Q implies P. So what does this mean? Well, this means that whoops. Where am I? I keep losing track of the little teeny tiny dot that represents where my marker is. If you see me randomly marking all over the place, that's what that is. All right. This will be true, of course. It rains, I wear my raincoat. We're good to go. It doesn't rain. Well, let me put it this way. It does rain and I don't wear my raincoat. Well, just like up here with our regular conditional expression, our regular implication, we're false. Now here's where the difference comes in. If it doesn't rain but I still wear my raincoat, now we're false. Because it says if and only if. I will only wear my raincoat if it rains. And then, of course, the case where both of them are false, were true. Because it didn't rain, so I didn't wear my raincoat. You can think of it, and one thing that I find useful when you're trying to spot these, because usually you're not going to see sentences that have the phrase if and only if in it. For the record, you'll see that a lot as IFF. That's if and only if. Can you do this? P implies Q, and Q implies P, right? If both of these are true, I like to think of it as you crush down. So you have P, you have your implication for Q, then you have Q, which in turn implies P. So you just overlay these arrows on top of each other and you have your if and only if. There's a technical name for each of these versions of the proposition. We'll get to that in a little bit in a different video. But the important thing to note here is that if P implies Q and Q also implies P, then you have a biconditional. You don't have an implication. All right, so we'll just quickly wrap up this particular video. We're running a little over half an hour now by my watch. So we started talking about a proposition, which is a statement that is both a declarative sentence and can be reduced to true or false, but not both. An example would be, it is raining. You can take a proposition, and because it can be reduced to only one particular value, be it true or false, you can assign it a variable. And using these variables together with connectives, you can string multiple propositions together to form compound propositions, such as P or Q. It will rain today or it will rain tomorrow. You can also use and not. And for if-then statements, you have the implication and the by implication. We also covered, sort of incidentally, this idea of a truth table, where you express your compound proposition in terms of your P's and Q's, your variables, along with the connectives in the middle. And then you can put that in a table like this, which goes together and lists out every possible value for P and Q, every combination of values, I should say, and then tells you for what combinations of values the compound proposition itself is going to be true or false. The number of rows in your truth table is dependent upon the number of variables that you have in your compound proposition. In the simple case here with a negation, where we just have one variable, P, there's only 2 rows. In the more complex case where we have 2, there are actually 4. The simple formula for the number of rows is, let me get some fresh space down here, 2 to the n, where n is the number of variables. All right, so that is it for this particular video. I hope that it was a little useful for you. It seems all very, what's the word I'm looking for, arcane, perhaps not arcane, but doesn't seem terribly concrete and useful at this point in time. But when we get into the next video and I introduce some slightly more advanced concepts of propositional logic, I think you'll start to see where it becomes useful and how it can really help you solve problems. And most importantly, how it can help you program, because this is the basis of program logic. Just to briefly mention this by implication here, the if and only if, this is what you would call your if statement in programming. If you know anything about programming, this is that particular relationship there. So I will see you in the next video. I hope that you guys all have a wonderful day, and catch you later.